Welcome everyone to the sixth video here on chapter 17. In this video, we're going to start talking about solubility product equilibrium. So, solubility product equilibrium, right, is related to solubility product constant, it's labeled KSP. So it's it's an equilibrium constant, right? Capital K equilibrium constant. And then we give this lowercase sp, right? This the subscript, right? Just indicates solubility product reaction, okay? Which is a precipitation. I'll often say participation or something like that. I make that mistake all the time, right? But a precipitation reaction or dissolution reaction of some sort of ionic compound. For example, here calcium carbonate, right? Can undergo this equilibrium to form calcium ions, carbonate ions, right? It has an equilibrium constant of Ca2 plus times CO3 2 minus, right? Which again, we give this subscript Sp here to indicate this is for this dissolution reaction, this solubility product reaction, okay? So that is what KSP is standing for, right? Again, it's just related with the dissolution of ionic compounds, right? Basically, right, so far, most ionic compounds we've talked about are either strong electrolytes, where they completely break apart, or they're weak acids, weak bases, right? Which partially break apart and establish an equilibrium, right? Now we're going to talk about weak electrolytes that are not acids or bases, okay? But don't fully dissociate. Okay, so right, the magnitude of K, like in any equilibrium reaction, tells us some stuff, right? The larger the K is, the more soluble that ionic compound is in solution, right? Sodium chloride has a very large KSP, is very soluble in anything, right? While calcium carbonate is has a very, very small KSP, so it's a relatively insoluble compound, okay, right? Right, and that's what forms your stalactites and stalagmites and caves and caverns and things like that, right? And so, right, the size of this equilibrium constant tells us a lot about the salt and its solubility. All right, so what does KSP tell us about solubility and things like that, right? First, let's talk about the difference between solubility and solubility product, and then their relationship, right? So solubility that we've talked about right back in chapter 13, right? We were talking about how much solute can dissolve in a solution to form a saturated solution, right? And we often gave solubility in terms of moles per liter, right? You could also express in terms of grams per liter, milligrams per milliliters, right? Whatever type of units, right? Where often you're talking about solute over solvent, right? Okay, whether or not it's grams or moles of the solute and liters or say milliliters of the solvent, right? And the solubility, right, can change depending on temperature and other such factors, okay? Right, well, the solubility product, okay, right, that is referring to an equilibrium constant for an equilibrium reaction between the solid and the dissolved ions in a saturated solution, okay, right, again, in a saturated solution, okay, right, and it's abbreviated KSP, right, and it itself is a unitless quantity, right, and again, remember, when we talk about the solubility of something, right, or right, where a saturated solution is, right, that's the amount of ions that I can put in solution, right, before I start forming solids, right, or when I've reached, right, it's the concentration of ions that are in equilibrium with solid in that solution, right, and that equilibrium, right, is related with this equilibrium constant expression, right, and so again, say that calcium carbonate example, right, Ca2 plus CO3 2 minus, right, the calcium carbonate example, right, the concentrations of calcium and carbonate in solution, right, right, are the equilibrium concentrations, right, in this KSP, right, so this KSP, right, calcium Ca2 plus times CO3 2 minus, right? Those concentrations, right, are the concentrations for a saturated solution, right? Because a saturated solution is a solution that's in equilibrium with solid, right? Which means, right, that these a saturated solution, these concentrations, right, satisfy this equilibrium constant expression, right? Right, because this equilibrium constant expression is related with having an equilibrium established between those ions and the solid in solution, right? And so, right, and so the solubility product and knowing what KSP is can tell us about the solubility of our ionic compound in solution, right? And if we know the solubility of our ionic compound, then we can calculate KSP. Okay, so these things are directly related to each other, and we'll see plenty of examples of this relationship and using these relationships to find one from the other. Okay. Note that the solubility product itself is constant except for temperature. Okay, temperature can affect what KSP is. Right. Finally, right, we'll talk about solving ions in solution, things like that, mixing things together, right? And often we might have some initial concentrations of different ions and wonder, will a solid form, right? And to do that, we need to calculate the reaction quotient, right? Let's say I add in solution, like calcium chloride, right? Which breaks apart into Ca2 plus Cl minus, right? 2Cl minus, right? And then I also add in sodium carbonate, right? Which breaks into the solution Na plus, right? Two of those, plus CO3 2 minus, right? I add both these things in solution, right? Well, now in solution, I have calcium floating around and carbonate floating around, which those can, you know, participate, there I go, right? Precipitate out of solution, right? Where I can have Ca2 plus, right? Plus CO3 2 minus, right? Forming an equilibrium with solid CaCO3, right? So I could get this equilibrium established in the solution where I could get out some solids, right? And so the question is, do I get it or do I not, depending on what concentrations of calcium chloride and sodium carbonate I add to my solution, right? And to solve that, we need to calculate the reaction quotient, okay? If the reaction quotient Q is greater than the equilibrium constant, right, that means I got too many products, right? My products are ions in solution, which means I got to form reactants. So I'm going to form solid, I'm going to get some precipitation occurring, right? And that's going to happen until eventually Q equals KSP and I've reached equilibrium and I've formed a saturated solution. Okay. If Q again equals KSP, then you're already at equilibrium, you've got a saturated solution, nothing happens. Okay. If Q is less than KSP, then you can dissolve more solid or more calcium chloride and more sodium carbonate, right, in solution until eventually you reach Q equaling KSP, right? So you have like an unsaturated solution if Q is less than KSP. So you can add more stuff until eventually you reach a saturated solution, which is when Q equals KSP. Okay. Right, and if Q is greater than KSP, you could think of that as like a super saturated solution, right? And then right, then the solid's going to start precipitating out very quickly from that solution.